All right, I think we're ready to go. Again, welcome back. Thank you, everyone who is here today. We won't do any more debug partying today. I think a better use of our time would be to continue our in-class topics today, and then I do have my office hours immediately afterwards, and my schedule is fairly free for that today. Um, so just stop in those, and it won't be live with the entire class, but I'm definitely happy to help you, walk through those things and just resolve some bugs as you go. Some groups I looked at their code yesterday, and it looks like you're making a lot of good progress. It's just a matter of finding the time to get it done at this point. I think once you get to the point where you have like a single instruction working properly, you should have picked up, I think, the debug skills at that point to say, okay, let's just keep adding more instructions. Let's just keep, working backwards from the result that we are being told is the case with what we see in our waveform and what we have in our code. And I haven't found the greater than 5 minute bug yet. It took us more than 5 minutes on Wednesday, but I was trying to walk through it slowly. So we can get past those, and you'll maybe have 20 or 30 bugs, and you have to just find them all and fix them all, and then you'll be done before you know it. Some reports that the synthesis step for the final design is taking hours and hours and hours and hours. That's actually a little hard to predict. That's something we talked about when I was synthesizing some designs, in the middle of class earlier this semester. Um, that's not a good thing. It's not supposed to be taking that long. That's not the intention behind that. It could just be an artifact of it running on those virtualized boxes where it's kind of pooled and shared resources, and they're only going to allocate so much CPU and memory and things like that for your particular job. Um, we'll experiment with ways to improve upon that. In a sense, that's kind of a minor thing. The synthesis tools will tell you pretty early on if there's something wrong with your code, if there's something they can't analyze, something broken with it that Model Sim didn't catch. You definitely want to fix and repair all of those. In terms of getting that final number out, um, it's not that important to me. So I want you to do it. There's points allocated for it. But certainly, finish the rest of your write up, get the rest of it done, move on to other things, let it run overnight if you can. That wasn't the intention for it to be a 7+ hour job for it to run and to synthesize. So hopefully not too many groups are seeing that. There will be a funny thing we will see for project part C if we get to that point. In that the synthesis will take significantly less time, even though there's much more logic in the design. And we can talk about when the time comes why that is the case. The tools actually have a much easier job of dealing with that design versus your single cycle processor design, just based on some of the architectural design decisions that we've made. And that's where we are in terms of our in class content here is dealing with those decisions associated with the pipeline processor. So on Monday we spent a lot of time understanding those data dependencies. And sometimes the terms aren't very consistent between one reference and another. There's no standards body that agrees on what every computer architecture term should be called. We were referring to it from the compiler's perspective and looking at read after write data dependencies. The type of hazard the textbook calls it is they call it a read before write data hazard. It's the same exact thing. It's we intended for there to be a read after write. That is the data dependency. If we don't build some extra mechanism to detect and prevent this from happening, the hazard, the incorrect state of our processor will be due to a read that happens before the write. So not meaning to muddle that too much. It's all referring to the same data dependency. It's all referring to the same exact scenario. And again, that scenario is um, that you have a register that's being written to in a certain instruction, and one or maybe multiple subsequent instructions later, there is a register that is being used by that instruction. It's the source register for that subsequent instruction. You can think of this as the producing instruction. This is the consuming instruction, or just writing instruction and reading instruction. It's the same concept here. And that's our dependency that's potentially leading to our hazards. And it's you can think of it as we graphically lay out the pipeline sort of from left to right here and progressing in time. Those hazards can be thought of as dependencies that are backwards in time. I need, and at least in our standard execution, I need the value of register 1 for this subtract instruction. I need to read it for our pipeline to operate properly. I need to read it before the correct value has actually been written. And that's why these are shown as being backwards in time. That would be the hazard, that it's getting a stale old value. We would have the wrong value. And we also mentioned that those load instructions can also do the same thing. it's really just yes, thank you. It's really just the same concept, but we'll see it's a slightly additional special case here that load word instructions um, are also writing to the register file at the end. Sometimes it's hard to see that when we look at our code because, which one's the load, which one's the store, right? Which one is reading, which one's writing. Well, the load word is writing to the register file, but it's doing it has to do more work first before it gets that result to write back to the register file. So it is the same type of dependency. It is the same read after write data dependency, and ultimately, it's just going to be a special case in terms of how we prevent it. That's the so-called load use data hazard. But it's not fundamentally different. It's the same type of data dependency. If we want to visualize what's potentially happening here as why it's different, well, it's because the value that we're going to write to the register file is going to take an extra cycle to get generated. For the ALU instructions, we actually know the value that's going to be generated right around here because the ALU is done with its work. And maybe based on that, you can start to see what this so-called forwarding solution is going to look like here. For the load word, it's similarly a backwards dependency in time between that register one in the producer instruction and the register one in the consumer instruction. But we don't even know what that value is until after we've loaded from memory. So we don't even know what that value will be until a full cycle later. But otherwise, it is just another example of register usage. So one approach, and my best prediction would be this is the approach which is as far as we'll get to with Project Part C this semester. If you've if you've looked at Canvas, I kept the entire same assignment. It's written up exactly the same way, and the grading rubric is the same. But I've decreased the points to reflect the fact that you're only really going to have 3 weeks to work on it. And I'll post an announcement once I have a very clear policy for how that's going to go. But as part of that for Project Part C, as you'll be implementing these pipeline registers to hold that state information from one cycle to the next, your first approach for testing it will be to do what we refer to as a software scheduled pipeline. And that would be one way to fix these data hazards. And that way to fix the data hazard is just to stall, is just to wait. If we know, or even if we don't know, if we want to be careful, we can say, well, we don't know how many more cycles we have to have after we've fetched this instruction to be confident that there isn't any data hazards. Let us just add as many stalls as are necessary to guarantee that that would never be the case. In this case, for the add followed by a sub instruction, there's two subsequent instructions for which there's that backwards dependency in time. So one way, via software scheduling mechanism, to guarantee that these hazards wouldn't occur for those ALU type operations would be to stall for 2 cycles. Either some hardware mechanism that stalls, or that's not even necessary for Project Part C to begin with, just inserting no ops. But as we already mentioned, that's just not very satisfying, right? Yes, you can have these instructions and then you can insert all these no ops. But if we don't really think of no ops as being valid instructions, right, they're not doing any useful work. We have a full pipeline, but it's full of at least partially, no op instructions that aren't doing anything to advance the logic of our program. We have resolved our data hazards, but I would say it's kind of a worst case scenario for our resolution approach here, right? We've done so, but there is definitely a hit on performance. We are still getting one instruction per cycle finished, but in this case, it's every third instruction would be a valid one. So what's the point, right? Why did we even make this 5-stage pipeline if we're having to wait for 2 cycles every time we fetch and try to execute an instruction? We're probably better off with the multi-cycle or some other approach if that was going to be the case here. But that is one approach. It's kind of the approach of last resort. If we don't have some additional mechanism to resolve these data hazards, and later when we look at those control hazards today, we can always wait. We can always stall and say, can't fix it. The only thing I can fix it is by letting time advance, letting this instruction progress while we stall the other instructions so that that arrow for the data dependency is now forward in time and not backwards in time any longer. But the other approach, as mentioned, is referred to as data forwarding. Um, there's some architectural mechanisms that we would require to build to get this to work in practice. But the basic concept is to first recognize, and I mentioned this briefly just a moment ago here, that yes, while technically that value of 1 is only written back to the register file in cycle 5. And that's why we have the potential dependency and the hazard that we're worried about. It's only written back to the register file in cycle 5. The actual value that is going to get written to the register file, whatever the result was going to be, is actually known quite a bit earlier, right? You see it in your single cycle implementation that the ALU result is a signal in your design, and then there's a bunch of other muxes that it has to jump through to get to your register file write data port. Well, in the pipeline processor, that's even more explicit because it's not just a series of muxes and wires. Now it's also two separate pipeline registers it has to get through before it can get back to the register file. But the actual value, the value that is eventually going to be written back into register 1, is knowable earlier on. So when we refer to something as being data forwarding, as an approach to forwarding data through the pipeline, it's kind of skipping to the head of the line. That'd be one way to think about it. That this instruction is eventually going to write register 1 back in that 5th cycle here. But we can also skip to the head of the line and recognize that it is possible the subsequent instruction may need to know this value before it's written back to the register file. And even though it's not written back to the register file, it is in fact being written to a register. It's being written to that pipeline register. We are storing it. It is a stable value in our pipeline. It's just not in the final register file here. So in data forwarding, we would be building some logic to detect when this would be a concern, would be a case that we would have to do this forwarding, and then recognizing that from the ALU's perspective, it doesn't really care where the data came from, right? It just takes two inputs and in this case does the subtraction operation, right? Ideally, it's coming from the register file, and we do read from the register file for this next subtract instruction, but we're then going to forward the data from the previous instruction on and skip to the head of the line there, such that, as we can guess, it would require additional muxes and extra logic for that. We would have an additional mux here that, based on this condition being detected, this read after write dependency being detected, and then again, that's not going to be magical. We have um, the verbal syntax to describe exactly what your logic would have to look for, and then you just have to put it into code. But based on that dependency being detected, we can just literally connect this wire, which these aren't separate wires here, right? Basically, we're connecting this wire back into here. Let me draw that because I think that's maybe a subtle point. So this diagram is showing logically what's happening when we're doing that forwarding. But those green arrows don't exist in your diagram, right? That's logically how data can potentially get forwarded through time to get to the value where it's needed in your data path here. The value is knowable right here. That's supposed to be the value. It's knowable. We know what that value is, or it's stored in a pipeline register. We only need the value. We don't actually need the value to be correct right here. It'd be nice. It would be ideal, I think, if the value was correct right there at that time point. But we don't actually need to know that, have that value be correct at that time point. We need the value to be correct when it's being fed into the ALU. It keeps doing that. Back. That's when it needs to be correct. So our forwarding path, the actual path is not this green arrow. That's logically how it's being forwarded. The forwarding path is recognizing that actually I just need the output of the ALU to also kind of feed back into my input of the ALU. Because the value is correct at that point in the pipeline. And if we think of this instruction in isolation, the value that's being stored in the pipeline right here is correct, whereas the value that's right here is incorrect. So we would just be adding a mux like anything else, right? Like our class mascot suggests, and we would be just checking that condition, checking that this is equal to this, essentially. And if that's the case, we would then forward that value back. And instead of taking the actual register file read value, we'd be taking mux forwarded value. And those muxes are going to exist in several places in the pipeline. And that's to your question, Nicholas, I think. Yes, there would potentially be a similar reason to have to do it for the second input as well. those paths are going to exist, and discovering them is a little tricky. It can get out of hand if we're not careful. Modern pipelines don't have statically declared forwarding paths like this, but in this case, there's a decent number of them, and then our trick is to determine when we should be driving the logic for those select lines for those mucks is active or not. When should we be selecting a forwarded value versus the straight line, straight ahead value, the boring, the existing value from the register file. And that'll be necessary every time we want to consume a register value in our pipeline. So that's certainly ALU input one, that's certainly ALU input two, and it's certainly data memory input as well, which is potentially also a register value. There's other places as well, right? So it does get a little bit tricky. If we have separate branch logic, where are we consuming that values for the branch logic? All those forwarding paths are things that we have to discover and detect if that's going to be the case. But to start with, at least conceptually, it's the arrows now can potentially be green because even though we haven't written the value yet when we need it for this next instruction, it is somewhere in the pipeline. It's going to be right here actually at this point, right? It'll have moved one cycle ahead, and so we can connect not just the path from here back to here. We would also have a separate path from here back to here. I don't know if you could see what I was trying to show there. We don't need a path back from the register file back to the ALU because that's our standard path, right? That's our forward path. But our backwards paths are output of the ALU after that pipeline register being fed back into the input of the ALU. And then likewise, and that's if there's a one cycle away data dependency that we have to watch out for. When the data dependency is 2 cycles away, we don't want the output of the ALU because that would correspond to the output of this instruction's ALU, right? We'd be off by 1. But we want what's at the data memory stage is what we'd want to be writing back into the ALU, into the ALU inputs. So there'd be multiple paths there. And we have to really just look at the data dependencies between instructions, making sure we categorize instructions by those that produce values and those that consume values. And then not only that, where in the pipeline they do that, because any one of those combinations or permutations, any one of those combinations of producing places in the pipeline and consuming places in the pipeline is a potential hazard and is a potential forwarding path. Load use is a little trickier though, and that's why I called it out as a separate example of the data hazard. It is still a read before write data hazard. It's a read after write data dependency, but maybe we can see why it's a special case now. Before, when this was an add instruction, the value to be forwarded was available right here in our pipeline. Or I think more precisely from the next instruction's perspective, it was available right here in our pipeline. Right? It was there. It was available by the time that sub instruction needed register 1, we knew what the new value was going to be. It had been produced already, it just hadn't been stored finally back into the register file. But now with our load word instruction, well, what's different? We do have the ALU output, but that's not what we're writing back to the register file for the load word instruction. We're taking the result of the ALU and we're treating it as an address to memory. We're loading the value from memory, and that's what we're connecting back into the register file. That's what this is our mem to reg type mux like that you're working on right now. But that's that connection happening here. We read from data memory, we then store that back into the register file. We could build such a path, and you will need to build such a path, but that path between a load instruction followed by the immediately next subsequent use instruction is still wrong, right? It's still backwards in time at that point. The value is just not ready yet. That's another way to look at it. This gives us like a +1 kind of forwarding, basically is what we're doing. But the value takes an extra cycle to become valid. So in this case, it is a special case. Not only is it a different forwarding path, right? From here to here, we should be able to do forwarding because even though register 1's not in the register file yet, the updated value is not in the register file yet, it is known in the pipeline at that point. So this is potentially a valid path. Again, more precisely, more precisely, the forwarding path looks kind of like that, right? That's supposed to be an arrow, but it's something like that. It's the output of the data memory stage is being forwarded back into the ALU from a previous load instruction now to this use instruction. But for this one, we could claim that we want to use that path, right? Because that path is a physical wired path in our design now that we've created. The path is there, but it's not correct still for us, right? It's still the wrong value. It's whatever was previously on that line from the instruction previous to this load word instruction, and that could be garbage, right? That could be anything. We don't actually want to forward that value. That value is wrong. It's not representing what will be stored in register one. So unfortunately, that's why we call out for the five-stage MIPS pipeline the load use hazards as being a special case, is we can't resolve it via forwarding. And this has implications on our performance, right? Because load produces a value that much later in our pipeline than a ALU instruction does, we don't have enough time to forward it back to the execution stage of an immediately subsequent instruction, of a load immediately followed by a use instruction. So that's going to require a stall. And there's a homework question that asks about this, but basically that's what you'll be doing, right? You can analyze the code and realize, well, how many cycles is this going to take? It's not as simple now as just counting up the number of cycles. It's 5 cycles to get started here, 6, 7, 8, 9 cycles to finish up 4 additional instructions, plus 1 cycle because we're going to have to stall this sub instruction by 1 cycle. By stalling that sub instruction by 1 cycle, and we'll have to talk about how we design such a thing, we're not getting rid of the instruction. We're just telling that instruction to wait. And to wait for 1 cycle, because 1 cycle later, the dependency will look like this dependency now. You can think of it as inserting a no-op. That's one way to think about it, but it's something we're then dynamically inserting into our pipeline versus the compiler inserting the no-op for us here. But it's conceptually, performance-wise, it's the same thing. By inserting a no-op in between the load word and the sub instruction here, we still have the load use dependency, but because it's 2 cycles apart, we can now resolve that with forwarding as well. Questions about that? How are we doing? Okay. So what does forwarding cost? Well, we need to add stuff is what it says here, and that's absolutely correct. We need to add stuff to the data path and stuff to control. That is true. Similar to what we were doing for the multi-cycle processor, now our control scheme for the pipeline processor, but before it was, but now because we have to support things like data hazard detection and forwarding, our control scheme is no longer static like it is for your project part B. Right? For project part B, I call that a static control scheme because based on just your opcode and function code, you can generate every single select line, every single control signal in your data path, right? It's your spreadsheet approach. Input to the spreadsheet, output is my control signals. For the multi-cycle, we saw that because it was a state machine and we're storing results, we have to have some dynamically generated control signals that change from cycle to cycle. For the pipeline processor, it's slightly different than that there's going to need to be additional control signals that are being generated based on the interrelationship between instructions. Maybe that's not surprising, but we have to be able to detect that, these, I lost it here, that these arrows exist, right? Or as we were doing it, on the handwritten, kind of hand-coded example, we need to build hardware to detect that these dependencies exist. And well, what is hardware, right? I mean, for anything, right? We want to check if that value is equal to that value. If register 3 in the destination field of this instruction, let me phrase that a little bit better. If the destination address of this instruction is the same as the source address of this instruction, that's a control signal we now have to generate. Not statically. Remember, that has nothing to do with the opcode, right? It potentially has something related to the other control signals in our design, but at least at first blush here, as we walk through the logic for this, if this field, those 5 bits, is equal to this field, those 5 bits, that is at least a potential forwarding condition. So the forwarding hardware, in terms of what it's going to cost, stuff, right? It's gonna require stuff, but that stuff is going to be comparators and muxes by and large. We're comparing state values inside our processor and driving muxes based on those results. We already have kind of a feel for what those muxes may look like, um, but those comparators are just going to be 5-bit comparators because that's what we're generally looking at for this, right? We're looking at our register encoding fields, which are 5 bits for MIPS. And it's as simple as that. If the register destination at this stage in the pipeline is equal to this register source or second register source in this next or previous stage in the pipeline, we have a potential forwarding path. Set the control signal for that mux to 1, and that value will become your input to your ALU. I don't actually. The textbook says if there's existing muxes like there is for ALU source B, make it wider. I would separate your muxes out entirely. It's the same in terms of logic usage at the end. You should have a series of forwarding muxes as the final input to your ALU and to your data memory. And then that's a separate, independent of all your static control scheme, which tells you here's what the input to the ALU should be, assuming no pipelining issues, assuming no hazards or data dependencies. Now let's add one final mux after that, and that's my forwarding mux. That allows you to test things that work without any forwarding whatsoever, and then forwarding just becomes a one-off case of all of your testing. Um, there's going to be a lot of it. If we're not careful, the number of paths that we discover and the amount of logic we're adding and the amount of muxes we wind up adding can get a little bit out of hand if we are not careful. The approach that I like to follow is, again, as I mentioned, is to look at all those pipeline stages that produce values, and then separately all of those pipeline stages that consume those values. And this is part of the design philosophy of MIPS. So this is not a happy accident of MIPS. That in MIPS, in the 5-stage MIPS implementation, there's very few of those. Our values are really only getting produced by our ALU stage, and for the load word instruction by our memory stage. And likewise, for our existing implementation right now, the stages where we're consuming values would be in the EX stage and the MEM stage. So any combination of those pairs is fair game. And Kurt, your question is absolutely valid. We have to be pretty careful about this in terms of where the dependency is, which mux that is corresponding to, and how those values get encoded. We can't fake that anymore. We'd be very careful to say for the I-type instruction, it's actually the RT field that's designating where the right address in our register file is going to be. I think 2 weeks ago nobody cared about that, but now you all care a lot about that because you had to get that to work for your tests, right? For Project Part B. So you're probably pretty familiar and aware of that right now. But yes, we have to be aware of that case. So it's a combination of our static control and our dynamic control. We'd have to use those signals. Well, first off, a pretty important signal would be reg write for the producer instruction. We only care about any of this forwarding if the producer instruction is actually producing a value. Yes, I know we can look at it and say, yes, clearly that's producing a value. Look, it's an add instruction. Well, we have to be a bit more explicit when we're doing it in our pipeline, right? We have to have some way to tell our data forwarding logic, we should be worried. we should care about forwarding for this pair of instructions. And those static control signals can help us determine that, right? We care about this value producing a value if it writes to the register file. We have a control signal that does that for us. We just have to keep track of that control signal where it is in the pipeline. Likewise, we have an instruction that is consuming a value here. Or for this combination, consuming a value here. We have to make sure it's very clear that that value is actually being read by this instruction. Is it an instruction that's actually using that register source or RT value? Or is it in fact an instruction that isn't using those 5 bits as a register at all? It's getting a little subtle here, right? But this load word instruction is encoding this value of 4 in the immediate type. You'd have to get pretty unlucky for this to be the case, but if you have the wrong immediate type, it's going to look a lot like a register address if those upper 5 bits have something valid in them. But that's not a register that's being written to. We have to actually make sure that for the pair of instructions we're looking at, what were the fields of the instruction that were relevant to those, and is it in fact either producing and or consuming those registers for this to be a valid forwarding path? The textbook, like in all implementation details, uh, gets you started down this path, but does not bring you home. I mean, that's very much the case. So you can start with, and this text, this is straight from this textbook. These slides, we'll talk about some of the paths and a couple of the gotchas. Um, Normally, I'd like Project Part C to be a full 5 weeks, and we're not going to get to it this semester, and that's okay. You're still getting your money's worth out of this semester's tuition, I think, for this class. But um, catching those extra edge cases is where a lot of the Project Part C time would otherwise be spent. If you at least catch the textbook cases for forwarding, that's still really good here. But there are a lot of those special cases to watch out for, and that's why I said it can get out of hand if not careful. Um, I always recommend, as opposed to just like your control scheme, as opposed to trying to have a perfect spreadsheet and then getting started, have something that's okay, implement it, see where the flaws are, and then revise that design approach. Same with the forwarding paths. You could spend weeks trying to get it exactly right, and you still probably will miss something. So do something that's maybe textbook that maybe gets you started, and then as you test, you'll discover that that catches some things and it doesn't catch some other things, and you just add extra components for those extra special cases that you would have there. But let's talk a little bit about the logic before we start to run out of time here today. Um, this is kind of the textbook version of that logic. Uh, One thing that automatically is going to be different then is we would actually have to forward the or pass on those register address values through the pipeline. Normally, if you weren't worried about your um, forwarding logic at all, you would generate those register values like RS, RT, and RD, right? Um, this isn't that great of a picture, but this will have to do. You would generate those values pretty early on in the instruction, right? In our decode stage, we would then fetch those values from the register file, and we'd be done with those values. RD we would still need because we need to write back to the register file later on. We can't connect RD right away to the right address because that's not the right place to do it. It would be, several cycles later we would need to be connecting that RD signal. But for the RS and RT, in theory at least, if we're not worrying about hazards here, we connect those values to the read address 1 and the read address 2 ports, and then we're done with them. But to implement our forwarding logic, we need to be able to again detect that this is equal to this. And to be able to detect that this is the case, we need to have this value we're going to keep in the pipeline anyway because we need it till the very end. But this value we would normally not keep in the pipeline. We have to make sure we hang on to that value. Store it as part of our pipeline registers because we need it potentially at least one cycle later than we would normally need it, potentially 2 cycles later in the case of a store word instruction. So in terms of this logic for doing this part, you would at least start by passing the register addresses down the pipeline and hang on to it. And there's a naming convention that I think if you follow, you'll have a little bit less pain as you implement this. This is the textbook's naming convention, which is, this is the name of the actual register. And you can think of it as a structured type. You can implement it as a structured type if you want in VHDL, but don't. Just implement it as a big standard logic vector. And um, this field, these 5 bits as stored in that pipeline register, and these 5 bits as stored in that pipeline register. And also stored in the subsequent pipeline register, the actual register destination. So those conditions for our data hazards would correspond to when those register values would be equal to each other. When an instruction that's in the EX/mem stage, that was cycle 4 of that add instruction in our example, when its register destination is equal to the RS or the RT, it could be equal to both, right? You could consume the register twice in a single instruction. It doesn't have to be one or the other. When it is equal to the value that's going to be read from my register file, and as the question already asked in the chat here, we have to also check that we actually want that value. I mean, that's important, right? Does the instruction that's in this stage here actually need this value, which is something we can check using ALU source type signals that you have for your immediate or R type instruction encoding. But if assuming we do need to read this value and we do need to read this value, if the register fields are the same, That's our forwarding condition. And you can implement that in VHDL as an actual equal sign. If this signal name is equal to this signal name, they're both 5-bit standard logic vectors. That would probably get implemented as a XOR gate or something like that. There's a lot of different ways you could implement it, but if each bit is identical, then I should output forward from, and you want to call that something as explicit as possible, forward RD from EX mem stage to ID EX stage. That should be then set to 1. Otherwise, it should be set to 0. There's a couple gotchas even with that very, basic example or straightforward example. We should only be doing that again if it's actually producing that value, right? Only if those producer register destination fields, because there's going to be something always stored in the pipeline for those, right? There's going to be 5 bits in our 32-bit instruction that no matter what the instruction is, there's a 5 bits that we pull off and call RD or RT as need be, only if it's valid. You could have a separate signal called, will RD value is valid destination register, but we already do have a signal that basically encodes that for us. There's no harm as you implement this, if it makes your design easier for you to understand and to read, in creating somewhat duplicate control signals, but the column in your spreadsheet for any new signal would be identical to what we already have, which would be read write. So for that instruction, only if it's writing back to the register file, is there actually a value that we need to forward on. And we should be a little bit careful. It's kind of a weird edge case, but only if RD for that instruction is not 0. That doesn't seem like a nice, fair case, to be perfectly honest. But it's weird MIPS, but it's certainly valid MIPS that if my instruction sequence was, let's see here, if it was add, I broke it. If it was an add of register 0, you'll take my word for it. If it was add into register 0, I shouldn't say that. I mean it's a valid instruction. It doesn't do anything we would ever want to do. Just to be on the safe side, we could do it like that. That's valid MIPS code. It's weird MIPS code. It's MIPS code that's there to like test your processor and break your processor, and you would never actually see it in any other instance. I don't know. No ops kind of get encoded like that, right? No ops are like a shift left logical of 0, 0, 0, but normally we don't always see that. The end result of this code in a correct MIPS implementation is 0, right? This value should always be 0 because by ISA spec, register 0 always holds the value of 0. If we are not careful, and it's not that hard, it's just extra logic we have to check for, and it is a weird edge case, and sometimes it seems like in this course I don't care at all about edge cases and I tell you to ignore them. Other times I say this edge case is really important. This falls somewhere in between, I guess. But if we were not careful, our pipeline logic is comparing RD field of that instruction to RS, and likewise RT field of this instruction, detecting that they're the same, and forwarding not a value of 0 onto those ALU inputs, but forwarding whatever 1 plus 2 is in our ALU. Because that still gets calculated, right? That gets calculated. It turns out it's never actually going to get written to anywhere because we don't write anything to register 0, or we keep it at reset, or we just implemented it with pull downs, however we want to do it in our design. But if we were to implement this logic, I guess kind of naively, where we're checking that register RD is equal to register RS in the subsequent instruction, we would catch that and we would forward on a value that we don't want to forward on. So we would need to check that. That's long story short with regards to that. Just check that that's the case. If the register that we're writing to is not 0, do all this forwarding. Because if it is 0, that's a MIPS edge case of it should not actually be written anyway. We could probably also figure that out via our static control scheme. Maybe, maybe. I don't think anyone's doing that now, where we look at the opcode but if the destination field is 0, we actually set reg right to 0. I don't think anybody's doing that right now. So this is the necessary kind of edge case detection of if its reg right is 1, but we're not actually wanting to write to the register file. That's that special edge case. That's when register RD is 0. And then finally, you can get a look at what our forwarding hardware could look like in your design. Um, this is a simplified view of just part of the textbook description of what's happening with your forwarding logic in our pipeline. Um, you have to be a little careful, I guess, as you're trying to build hierarchy within your design. Don't overdo it for the pipeline processor because you're going to have these components like the forwarding unit that don't really sit in any stage. Other units, you can clearly say, well, the data memory's in this stage. You could create a block that's called data mem stage. I actually don't recommend doing it. Have it be a little bit messier because you're going to have these blocks that don't really fit in any given stage. But it's just going to be a separate functional unit that's going to take in, and it's not showing all the inputs here. It's going to take in some of your static control signals because we do need to know something about the instructions we're referring to. Those are coming off your pipeline because they're based on where each instruction is in the pipeline, and it's also grabbing those register values, right? Those register encodings of both destination registers of previous instructions and source registers for subsequent instructions. And the end result is just control signals for muxes. Select lines for muxes. In theory, that's straightforward in some sense. The devil's in the details as you implement it. I think you'll find with forwarding, it's a very common thing where the textbook gets you part of the way there, and definitely not all of the way there. Um, this example would be a common one that can really trip people up. So we're adding to register 1, and perhaps we're also, this code isn't doing anything interesting. I get that. Then we're also using that in that value 1 and then writing to it. And then finally, we are again reading from that register 1. As we talked about on Monday, there's a million data dependencies here that you could circle of the read after read and all that. But we care primarily about those read after write dependencies, of which there are a number. Obviously, we have our write to register 1 followed by a read. And that logic that we've just built should be able to detect that exactly for us. But we also have an interesting data dependency on this register 1. Okay, interesting is relative. Moderately interesting data dependency on this register 1 here. And it's a little different than the previous examples because it's kind of a double data hazard in a sense. And maybe you can see that, right? That we have both the immediately antecedent instruction producing a value that it's reading, and we have the one before that as well. And as we were seeing in our graphical layout of the pipeline, both of those are forwarding cases. Those are both data hazards we have to resolve via forwarding. Can someone tell me why is this a different case than what we just covered? It's very, like I said, it's interesting that's your mileage may vary on how interesting this is, but it is a case where the textbook mentions it kind of in a footnote, and then you definitely have to get this to work because this is, again, just like those other examples, this is not a highly unusual sequence of code. This isn't, I would say this one is, right? You won't see this by and large if you're writing normal code, but this one you'll see. It's very common. We have a variable and we update it and we want to update it again, right? So that you'll have 2 producing instructions to the same register in a row, followed by a consuming instruction. Not entirely right there. 2 cycles, it does have to do with the 2 cycle issue. Another way to phrase my question here is we already we've already talked just briefly now about the hardware needed to fix this. That's our forwarding path from the EX-MEM pipeline register back into the ALU input. And we separately have the hardware or the condition to fix this. That's a forwarding path from the mem/writeback register into the ALU input. But what makes this case different than the previous case? It is Friday, and that's okay. We'll have a sufficiently awkward silence for as long as it takes. Let's go back to this logic. Uh, and I don't really know. I don't really know if you can see the logic in this, but the logic equations for it. Ignoring the register zero, here is our logic. If the and it's register RS in both cases, right? If this is true, forward from the EX-MEM pipeline reg. If this is true, forward from the mem/writeback pipeline reg. What becomes the issue with this case? Ah, there you go. That's a good way of phrasing it. Both of you have a good way of phrasing that. More important, yeah, that's fine. Has to take priority is what. So just to rephrase that, the more recent forwarding, the more recent producing instruction has to take priority over the older producing instruction. In this case, the one that's outputting from the EX mem register has to take priority over the forwarding case that corresponds to the mem/writeback register. So our logic also, we talk about the special edge cases that the book kind of winks at and mentions very briefly. In this case, we have the logic for both of these, but there has to be some priority encoding mechanism in which if both of those cases are true, we only take the one from that sub instruction and not the one from that initial add instruction. And I think from a logical correctness perspective of our code, that makes some sense, right? We write this code, we want the output of this instruction to be what is used in this, not the output of this instruction. That's an old stale value. Nothing has been written back to the register file yet. They're both potentially valid forwarding paths. We have to take the most recent one. And in our MIPS pipeline processor, it's not so bad because there's just two possible places we are forwarding from. As your pipeline depth grows, the number of places you can produce values grows quite a bit. You tend to see modern microprocessors that have larger pipelines, as is often the case. They have dedicated logic for keeping track of the registers in your pipeline, so-called scoreboarding logic that keeps track of where all the data is in flight in your processor. Because the number of those paths, the number of edge cases, grows significantly as you increase your number of pipeline stages. Let's leave things here for today. Um, Everyone's got a lot of work to do this weekend. Go trick or treating. Go have some candy. Go. Relax briefly in a socially distant and pandemic safe way, and come back. Tomorrow morning, raring to go and work on project part B. I'll see people in office hours if they want to help with debugging anything. And otherwise, good luck with that, and I will see everyone on Monday.